So now we have prime factorization. Very fancy. This is going to be very similar to what we were doing with the factorization. Here, though, the point is to break everything down as much as possible. And the results that you end up with when it's as much as possible are prime numbers. So a prime number is a whole number greater than 1, meaning 1 is not prime. If you had a teacher tell you 1 was prime, they made a boo-boo. You did whatever you had to do to pass their class. Now I am here to tell you, at least according to this book, 1 is not prime. Honestly, that is one of those things mathematicians debate when they're drunk. Is 1 prime? Well, it depends on how you write your book. Mathematicians are kind of funny drunk. It's like drunk history, but weird. All right, so for our purposes, 1 is not considered prime. 0 is also not considered prime. Negative numbers are not considered prime because it has to be whole number greater than 1. If you take out the greater than 1 part, you get a couple extra in there. It gets a little weird. So for ours, the smallest prime number is 2. And 2 is also the only even prime number because every other even number is divisible by 2. Now, a composite number is a whole number greater than 1 that's not prime. I know that's like a cop-out answer, but it is a number that will have at least one factor other than 1 in the number itself, meaning there's a number, a whole number between 1 and the number itself that will divide nicely into the number itself. Which means a composite number can be broken down into prime factors, because if they're not prime, they're composite, and then you can break them down again. So eventually that breakdown has to stop at prime numbers, because if it could keep going, we'd keep going, but eventually it has to stop. So the whole numbers 0 and 1 are neither prime nor composite because our definitions specifically exclude them, because the definitions are written depending on the numbers we're talking about being greater than 1. Every whole number greater than 1 can be written as a product of prime factors. When we write a number as a product of its prime factors, it is called the prime factorization of the number. Sounds like the prime directive for mathematics. Except instead of leaving people alone, we mess with everybody. All right. So, first one is 9. I know 9. One-digit number, but I know 9. 9 is 3 times 3. So the way a lot of people do prime factorizations is with what's commonly called a tree diagram. It's where you draw this branching structure. That's the way I usually do it. And then underneath it, I pick a pair of numbers, whole numbers that are not 1 in the number itself, that multiply to the number. So 9 is 3 times 3, so I write the 2 3s. And now 9 is no longer an end point in my factor tree. That's why I was gesturing like up and down, because all the ends of the factor tree are going to be where our prime numbers are. So 9 is the same as 3 times 3. So 9 is composite. All right. Now, 23. That one's a little bit weirder. It's not even. I'm not going to get 3 in there. 2 plus 3 is only 5. So since 2 doesn't go in there, 4, 6, 8, 10, any other even number will not divide in there nicely. So we're just going to think about odds now. 5 won't work. We hate 7, so for me to check this, if the number's not small enough for me to know it's not, I will 23 divided by 7. Enter. 3 point ugly ugly. Okay, it's not divisible by 7. 8, no, 9. If it's not divisible by 3, it's not divisible by 9. But with the 7, we already got 3 point something. We've passed the mark where we need to check those. So let me run through what the actual numbers are so you guys can see like what's the point you need to stop. So 23 divided by 2 gives us 11.5. All right. So 2 times 11.5. 11.5 is not a whole number, so this is not a factorization, but it is two numbers that multiply to 23. So that is our first prime number that we would check. So now we're going to back that up. We're going to do 23 divided by 3. And that is 7.666666, or 7 2/3, if you will. All right. But again, not two whole numbers. So this is not a factorization, definitely not a prime factorization. 2 doesn't work, so 4 won't. But we could try 4 just so you can see what size the other factor would be. And the other factor would be 5.75. So you remember before when I was talking about trying the whole numbers, and then once there's no more numbers in between that you haven't checked, you can stop? That's what this is telling us. If I check 5, I get 4.6. I've looped back around. So there are no prime numbers smaller than 23 that will divide into 23. So 23 is prime. Now I know the explanation there is a little weird. You could legit just take every number between 1 and 23 and check if they divide in there. And they don't. But this is a way that's a little more streamlined, so you don't have to check every single number. So I start with 2 and I just start going down the list. And then once the result I get is smaller than the number I was dividing in, I don't have to check anymore. Because if it was going to be there, it would have showed up already. All right, 59. Well, it's not 2 and it's not 5. And 9 plus 5 is 14, which is not divisible by 3. So if it's not 2, it's not 2, not 3, not 4, not 5, not 6, 7. So one of my often forgotten math facts that my dad taught me. This is the last single by single digit math fact that I had to remember. 4th grade. I hated this fact. I could not remember it. It made no sense. Like I was always like, okay, 7 times 7 is 49. And then do I add 7 to that or 8 to that? I'd confuse myself horribly. You add 7 to that. To get 8 sevens, you take 7 sevens and add another 7. But 8 times 7 is 56 because it goes 5, 6, 7, 8. And now I have shared that wonderful tidbit with you. So if you have any nieces or nephews or kids who at some point are practicing their multiplication, teachers should not do kill and drill anymore. That's been research proven. It's not a good way to learn. You just practice until everything gets more fluid. But this is a way to remember it while you're getting that fluid practice. And some of you guys are like, oh my God, would she just shut up and go on with the math? I'm sorry. ADD brain. All right, so pretty sure here 59 is also going to be prime, but let's check some of the weird ones. So 59 divided by 7 gives us 8.42. Yep, so it's prime. Since 2 won't go in there, 8 won't go in there. Now, 4, 5, 6, though. 4 and 6 is 10, and 5 is 15, so 3 is going to go in here. Alrighty, so we would have 3 times, and because my calculator's already out, 152. Oh, well, that's not a surprise. We had the 6 in there at the end, so this is divisible by 2. Now, I'm doing 152 divided by 2. I have my 3 as a stopping point. I don't need to consider 456 because I've changed that into 3 times 152. So I would, 3 is going to be one of the numbers in my prime factorization. Although right now, all they asked is it prime, composite, or neither? We have enough to say it's composite. But if we were actually going to work the prime factorization, let's go ahead and keep going. So 152 divided by 2 is 76. So there's the next digit in the prime factorization. And then we're going to check that 76 some more, still even. We get 38. Still even. And we get 19. Now 19 is prime. So we can stop there. Nothing will go into 19 besides 1 and 19. So that is our prime factorization. 456 is the same as 3 times 2 times 2 times 2 times 19. Usually we put the numbers smallest to biggest, so we'd usually say 2 times 2 times 2 times 3 times 19. Really doesn't matter. But again, definitely composite. And then 1. And remember, we left the neither because 1 does not fall in the permissible numbers for prime or composite, so it is a neither. If they gave you a negative number, which I don't think they will, but if they did, you would also say neither. They give you 0, you say neither. If I was writing a test, that would be a test question. So giving you a couple of these numbers and just tell me if they're prime or composite. So you can use your divisibility rules to speed that up, or you could just use your tools, use your calculator. Someday I will get the rest of mathematicians to believe me that we need to change the way we teach. Okay. Now we're going to look at 17 through 21. So 17 and 18, determine whether the factorization represents the prime factorization. If it does not, explain why. Oh joy, a math question asking for words. It's okay. So we just have to be able to articulate in some way, shape, or form. Doesn't necessarily have to be grammatically correct. It just has to be something that I understand what you were trying to say. All right. So 98 equals 2 times 49. So the math trick question would be 2 times 49 isn't actually equal to 98. They're not going to do that here. That's not the kind of, is this the prime factorization question? It might happen on some of your teachers in the past may have written questions like that. The math textbook generally does not. So 2 times 49, is that a prime factorization? To be, and it's there is only one way to decompose a composite number into primes. So is that the prime factorization? 2 is prime. Is 49 prime? Well, it's not divisible by 2 or 3, so no 4 or 5, so no 6, 7. Hopefully you remember your squares. 49 is 7 times 7. 7 is a prime number. 49 is not a prime number. So 98 equals 2 times 49 is a factorization, but it is not the prime factorization of 98 because it was not a product of nothing but primes, a product of only primes. They still had a composite number in there. But this was kind of confusing the two definitions we talked about. So we talked about factorizations that had two numbers being multiplied. That got us back to the result, which this is. And then prime factorization said you had to decompose into prime numbers only. What they ninja left out of that definition is it doesn't have to be just two numbers. It can be however many it takes as long as those numbers are prime. Okay, so this is no, because the 49 can be broken down more. On 18, 60 is 2 times 2 times 3 times 5. And 4 times 5 is 20, 3 times 20 is 60, so it does check. So 2 is prime, 3 is prime, 5 is prime, so this is the prime factorization. Now I say it like that, meaning I could take different steps, but any which way I did the breakdown of 60, this is my answer if I arranged it smallest to largest. There is no other set of numbers that are all prime that will multiply to 60. So that's one of the reasons why we like the prime factorization, because it's kind of like the number's unique thumbprint, as it were. You can't change it. That 2 times 2 times 3 times 5 belongs to 60, doesn't belong to anyone else. All right, so now, just like we did earlier, we're going to find the prime factorization, the actual tree diagrams for these. There is another way to do it. It's called a ladder diagram. And it looks kind of like an upside down division number. But when you do a whole bunch of them all stacked together, it kind of looks like a ladder. So that's why they call it that. So I'm going to show you that look because it can save you a little bit of paper. So 50. And if I had more space there, I'd put it there, but I don't. So 50 is divisible by 2. 2 goes into 50 25 times. Then 25 is 5 times 5. And those 5s are now prime. So my prime factorization are those numbers outside. The tree diagram is in there. 50 is 2 times 25. 25 is 5 times 5. We've just turned the thing on its side and made sure the numbers lined up. So 2 times 5 times 5. Now, if you accidentally typed that in the wrong order, maybe instead of starting with 2, you started with 5. That's fine. The big catch here is the numbers that you write down on the outside need to be prime. Like I know 50 is divisible by 10, but then you would need to break down the 10 rather than the 5. So you have to be a little more careful about what numbers you put on the outside because we don't have a good way in the ladder diagram of breaking down a divisor. I think it's divisor. Mathematicians never remember the difference between those words. We all have to think about it. All right. So 264 now. That's going to be big. So that's 6, 7, 8, 9, 10, 11, 12. Ooh, it's divisible by 3. It's also divisible by 2. So I usually start with 2 because it's smaller. So 2 goes into 2 once, 2 goes into 6 3 times, 2 goes into 4 2 times. Still even. Do it again. 2 does not go into 1, so 13. It's 12, so 6 times with 1 left over for 12, so 66. Oh, now we're getting somewhere. So 66, hopefully you're familiar, you're comfy with your 11 times tables, but seeing same number, just the pair of the same numbers, it has to be divisible by 11, and 66 is indeed 6 times 11. All right, so I have 2 2s, a 6, and an 11. The 11 is prime. The 2s are prime. The 6 is still not, though. So we're going to break that down 3 times 2. All right, so the prime factorization is all those what I call terminal numbers, the numbers that are prime, so you cannot break them down anymore. Now I want you to know I put the 6 here before the 11. The 6 was not prime, but in the tree diagram, I could break it down right there and keep going. So it doesn't matter where in the tree I am for breaking down my numbers. Like I don't have to always write the non-prime number on the right. In the tree diagram, you can actually write them wherever you want. And you don't have to necessarily start with 2 times something. I could have started with, let's see, 2 times 2 times 3 is 12. So I could have done 264 and done 12 times, and I have no clue what that actually is. So we're going to use the calculator. Oh, I think it's 22 actually. 264 divided by 12 is indeed 22. And we're going to get the same prime factorization. I'm just going to work it out to show you guys in the hopes that you will then believe me. And I'm going to go with 6 times 2 here and 2 times 3. So we check it out. We have 1, 2, 3 2s, a 3 and an 11. 1, 2, 3 2s, a 3 and an 11. So that is what 264 is. 2 times 2 times 2 times 3 times 11. If we write them smallest to largest, either list I work from, that is the numbers once I put them lowest to biggest. Now, some people, the 2 times 2 times 2, you might have vague memories of exponents. And exponents are, mathematicians are lazy and they don't want to write 2 times 2 times 2. They want to write something smaller. So after getting tired of writing that over and over and over again, they were like, okay, we're writing 2 a whole bunch. Let's just count how many times, and then we'll put that number down. And somebody said, well, wait, you can't just put it next to it. Then it looks like times. And that's what we've been doing. You can't do that. Okay, we'll put it above. And thus were exponents born as a mathematicians are lazy shorthand. So 2 times 2 times 2 can be written as 2 to the third. It does not have to be, though. And since we haven't really talked about exponents yet, I don't expect you guys to. I'm just throwing it out there in case that idea was in the back of your mind, just to be like, yes, that is an idea that should be associated here, but it's okay if it's not yet. And then our last crazy one here, 308. Well, it's even. And in fact, the last 2 digits are divisible by 4. So let's figure out how many times 4 goes in there. So 4 would go into 30, 28, 7 times with 220 left over. And 28 is 7 times. Oh, so we get 4 times 77. Well, we know the 4. 2 times 2. 77, just like the 66 from before, 7 times 11. Now, the prime factorization, it always ends with prime numbers, and it gets really boring if it's just 2s and 3s. Sometimes they'll throw in a 5, but that gets kind of obvious. So usually to make things interesting, you're going to see 7s, 11s, and the occasional 13, maybe a 17 or a 19. We saw that earlier, but it only went like 3 levels down. So there is our prime factorization for 308. 2 times 2, which could be written as 2 squared, times 7 times 11. All right, so we're going to cut this one here, and then I will come back talking about the equivalent fractions and simplifying them.